All right. Well, hi. This is Unit C-02. I'm recording this on a Sunday evening, and you can tell I'm in my classroom. So yes, I did come up to the school so I could record these videos. I'm hoping to knock out everything, but we'll see how far I get on that. Okay. So this is the video. Okay. So here's the notes packet, right? Okay. Like I said, as you probably have noticed in the videos, I'm just going to blaze through it, okay, because you can always pause it, you can always move it faster, you can always make it slower, right? Whatever you need to do, you can always pause it, stop it, whatever. I do encourage you for every single example to try it on your own before you actually start, before you actually just look at what I got, okay? So first off, there's two types of electric charge, okay? And this shouldn't be like a surprise to you at all. There's two types of electric charge, and they are called positive and negative. Okay, and I usually use positive as blue, negative as red. Okay, now it's important to note that even though you can think of it like, maybe you have some object that's charged, right? There's no natural object that has all of one type of charge. Okay, so when you think of an object that's charged, right, if you think of like a rod maybe that's charged, or even an atom, like if you're thinking in terms of chemistry, when it's charged, okay, it's not that it only has positive charges or that it only has negative charges. It's rather that it has have more of one type of charge than the other. Okay, and you can't really tell what that says. It says of, okay, have more of one type of charge than the other, okay? So if you have more positive charges than negative, then you have a net positive charge. If you have more negative charges than positive, you'd have a net negative charge, okay? Charges attract or repel. They repel if they have like sign, okay? But if they have the same sign, or if they have, the opposite sign, they attract. Okay, you've heard the saying opposites attract probably, okay? A charged object can attract an uncharged object, and it's kind of hard to demonstrate, so I'm not really going to do it here, but if you take like a balloon and you inflate it and then you rub it against your head, okay, then you would actually be able to observe this phenomenon. But it's called polarization. Okay, through polarization, the charge, so if an object is neutral, right, and it has an equal number of positive and negative charges, right, and these charges are able to freely move about the surface, which in some objects it can, some objects it can't, okay, it's where the charges in a neutral object, okay, separate, okay, then the opposite sign charges, okay, cause attraction. Okay, so if you have, for example, like I said with the balloon, right? If you take the balloon and you rub it against your hair, it'll become negatively charged, okay? It'll become negatively charged because what's going to happen is when you rub it against the hair, the electrons from your hair are jumping onto the balloon, okay? So the balloon will become negatively charged. If you bring it near a piece of paper, you're going to notice that the piece of paper starts to float up towards the balloon, because what's happening is the paper is neutrally charged, but the positive charges on the paper are being pulled towards the negative charges on the balloon, and it's going to cause an attraction. The reason it causes attraction and doesn't just cancel out is because you'll notice that the electric force between two charges is weaker the farther the two are. So the repulsion force between the like charges is a lot weaker than the attraction force between the charges, okay? What do you call an atom that has a net electric charge? You probably remember this from chemistry. You can call it an ion, okay? And an atom becomes positive if you remove electrons, and it becomes negative if you add electrons. Okay, we don't ever mess with the protons or the neutrons. We only mess with the electrons, right? You probably remember that from chemistry, how if you have an ion, right, it just changes the number of electrons that are on the object, okay? Okay, let's talk about conductors and insulators really quickly. You probably know them in terms of temperature, like which ones are good conductors of heat, which ones are good insulators of heat, okay? A good conductor, okay, in order for an object to be a good conductor, okay, the charges need to be able to, the charges are can freely move around the conducting surface. Okay, the charges can freely move around the conducting surface, right? So this means, for example, something like a good conductor would have, the charges are able to scatter around, right? So they're able to shuffle around really easily. So some examples would be, good conductors would be something maybe like metals, okay? Ionic solutions, copper, right? You can think of, well, I guess copper is a metal, right? But you can think of a bunch of different things that are probably good conductors for electricity, okay? And then an insulator, on the other hand, is going to be the opposite of that. So instead of the charges being able to freely move around, they're kind of fixed in place. So charges fixed in place. Charges fixed in place and cannot move. Okay, so the charges are fixed in place and cannot move. Some examples of good insulators might be something like wood, okay, glass, plastic, okay. You could say rubber. Even pure water is not a super great conductor. However, if you've done the resistivity lab, right? We did the resistivity lab in Unit 1, where we ran a current through tap water. You'll notice that tap water is not pure water, right? There may be minerals in there that, or there may be minerals in there that make it slightly more conductive than regular water, right? If it was pure water, the current may not have been able to flow as easily through the spoon with the water in it, okay? Okay, let's talk about polarization and electric dipoles. So basically, polarization we briefly talked about already, but basically what happens is that the positive and negative charges in the object are going to separate. So the positives, okay, and negatives, and I'm trying not to use blue and red, and negatives in object separate. Okay, what they do is they separate, okay? So the object is still neutral, okay, but has a positive, but it will have a positive and negative side, okay? Okay, there's a positive and a negative side. So there's maybe, for example, like on the pieces of paper, right? The piece of paper that's facing the balloon in that example that I explained earlier, piece of paper that's facing the balloon would be positively charged. Piece of paper that's opposite on the opposite side would be negatively charged. Okay, there's a dipole molecule that you're really familiar with, whether you know it or not. You probably learned this also again in chemistry, but it's water. Okay, you can test this because if you hold a charge object up to a water stream, it bends, okay? And you can't really, and I can't show it to you in the video, but you can find videos of it. You could just do like water dipole demonstration where you would see that if you have like, a sink or water coming out somewhere, right? And then you bring a charged rod near it, you can actually bend the water stream because the water molecules have a positive and a negative side, and they'll actually turn to be attracted to the rod, okay? And that's how it works. Let me explain how an electroscope works. So you do have a performance test where you have to build an electroscope, okay? And it's pretty straightforward how it's built, okay? You have a container, okay? And then you might have like a ball or a sphere or something at the top here, okay? And then that ball or sphere connects into the container, and it's got a stem, and then there's usually some little foil leaves on it, okay? So these are leaves, and they're made of metal. The stem is also made of metal, okay? The sphere doesn't have to be a sphere. It can be like a circle or something, just something that can sense the force, right? The sphere is a metal as well. Okay, the container is not necessarily metal. In fact, it shouldn't be. Okay, so what happens is initially the electroscope has a neutral charge distributed throughout it. But what happens is if you bring, let's say, a rod that is negatively charged near the electroscope, then you're going to notice that what's going to happen is along the sphere and the stem and the leaves, there's all these positive and negative charges. Well, the positive charges are going to see this here, and they're going to go, oh, I want to be near the negative charges, right? So boom, 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 okay? All the positive charges are going to go up to the top, right? The negative charges, they don't want to be near the negative rod because they repel, so they're going to go down to the leaves, okay? Boom, 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 okay? And you get negative charges all on the leaves. But then what you notice is that each of the leaves are negatively charged, which means they are repelling each other as well. So you'll notice that what happens is that when there's no charge detected or no electric field present, the leaves are going to be just kind of free hanging, but when there is an electric field present, the leaves will separate, okay? And the reason for that is because the leaves have the same charge. Have same charge, so they separate. Okay. Okay. Is the human body a conductor or an insulator? What evidence do you have for the assertion? So the human body is actually a really good conductor. Okay. It's a great conductor. Why? Because you are able to shock yourself or other people, right? It's a good conductor. Okay. You can be shocked, okay, by static electricity. Okay, now the reason why that's evidence for the assertion is that if you were not a good conductor, so if somebody rubbed their feet on the carpet and then went up to you and touched you to shock you, right? If you were not a good conductor, that electricity would not jump to you, okay? Because it wouldn't be compelled to go to you, right? Because you would be an insulator, you wouldn't want to get the charge, and you can't have them move around. The reason the static electricity, why you can shock people, right, is because the charges on our body can freely move around, and so we're basically freely moving around the charges on their body, right? Okay, what does it mean to charge an object by contact? This is where charges move from one object to another, okay, because they touch. Sorry, I shouldn't say they, I should say the objects touch, okay? The objects touch, right? So if you have two conducting spheres, one of them is positively charged and the other one is negatively charged, you touch them together, you can actually you'll actually charge the uncharged one, okay? If it's by induction, this is where they're able to be charged without direct contact, okay? Charges move when object is held near but never touches a charged object. Okay, held near but never touches, okay? So if an object is held near but never touches it, you can kind of charge it through induction. Oh my gosh, I see a lizard on my wall right now. There's a lizard on my wall above the cabinets. Okay, that's whatever. We're gonna move on from it, but I'm gonna keep an eye on it because I'm suspicious of it. Okay, anyways. To ground an object or a charge, right? You may hear this term grounding, right? To ground an object or a charge is when you connect the object, to something really big. Okay? In most cases, that's the Earth. Okay? and then the charges escape. Okay, and then into the big thing and spread out. Okay. So for example, if you have a charged object and you ground it, right? So let's say you have a charged rod. This probably, it doesn't really work exactly like this, but let's say you have a charged rod, right? And you ground it, okay? What's gonna happen is all the charges on the rod are going to escape from the rod into the ground, into the earth, okay? And now instead of them being constrained to this rod where it's really, where it's where the charges are more tightly compact, now they have the whole earth to go, which is a really big space for them because they're teeny tiny little charges, right? Objects can discharge, right? If it's humid, you may notice it's actually harder to do electrostatics demos when it's humid. Okay. And the reason is because what happens is that there's water molecules in the air, especially when it's humid, right? The water molecules in air, okay, randomly bounce off of the object. Okay. The H2O molecules, when they collide with the object, they kind of grab the excess charges off of them. So if the object is charged, H2O molecule comes in, boom, takes some of the excess charge, and then leaves, right? And this is happening over and over again. The more humid things are, the more molecules there are, which is the greater chance of this phenomenon happening, okay? And when we say that charge is quantized, this is also really important, right? Another word that we can say for it is discrete. Okay. Okay. And antonym, another word, a word that is the opposite of that would be the phrase continuous. What this means is that so when we say that charge is quantized, we mean that the allowed amounts of charge are multiples of a base value. Okay, so think of it like this, okay? When charge is quantized, that means that it has to be multiples of a certain base value, which in this case is the elementary charge, okay? If you remember the elementary charge, it should be little e is equal to 1.6 times 10 to the negative 19 coulombs, okay? And so when we say that charge is quantized, it's multiples of that. It's because we can't have half electrons or 3/4 electrons or a quarter electron or a 1/12 of an electron. We have to have one full electron, okay? You can't have half or parts of an electron. It has to be either a full electron or not. So if each electron is this much charge, then you would just multiply this charge by the number of electrons in the object, right? Okay. That's part one. Okay, we'll be back with what's next? Static electricity. Yeah, static electricity. Okay. All right. See you then.